Howdy, this is an introduction to invalidity in predicate logic. You can visit my website, by the way, at amateurlogician.com, and there you can support my work, which will allow me to continue to make videos like this. It's important to realize that there are different levels of language. For example, there's a level dealing with the form and structure, of language. This is the syntax. Consider grammar. Grammar deals with the form and structure of language. It deals with the rules governing a sentence in order for it to be coherent. You have to follow certain basic rules so that your sentence can even make any sense. Another level deals with the meaning of language. This is the semantics. What does a given word refer to? What does a given word mean? Another level deals with the manner of expression. This is the pragmatics. Consider tone. Tone can alter the meaning of an expression. If I say a sentence in a sarcastic tone, that can mean something quite different than if I don't do so. Now, formal logic only deals with the first. It deals with syntax. Informal logic can also deal with semantics, but that's not our concern right now. That is, in formal logic, we are dealing with the general form and structure of language as it pertains to propositions and arguments. It is a purely syntactic content. And because it is a purely syntactic content, we can use very abstract symbols. For example, consider, say, modus ponens. Now, modus ponens is a very abstract thing. We could write it down as if P, then Q, P, therefore Q. But that can represent all sorts of different content. Okay, P can represent all sorts of different things. Q can represent all sorts of different things. In any case, we want to think about invalidity. And one way we can do this is just to consider the different possible combinations. So let's say we know for a fact that we have all true premises, or all false premises, or a mixture of true and false premises. And also consider the conclusion. It could be either true or false. Now, if you think about it, there's really only one combination we know for sure, where we know that the argument must be invalid. That's where all the premises are true, but the conclusion is false. Then the argument must be invalid. Otherwise, you have something that can be valid sometimes and sometimes invalid. It's simply left open. For example, consider the possibility that we have all true premises and a true conclusion. Does the argument have to be valid? No. It could be that the conclusion is true just by accident. Okay. It doesn't mean the argument must be valid. But in any case, in predicate logic and also in propositional logic, the basic goal is to say, hey, look, we know that in this given argument, we have all true premises, we have a false conclusion, so it must be the case that the argument is invalid. One way to show invalidity is through the counterexample method. So first off, we have an argument we believe is invalid, and so, secondly, we will substitute uncontroversial semantic content in it with ordinary language to show invalidity. That is, first, we will substitute semantic content in such a way to have true premises, and we will substitute semantic content in such a way to have a false conclusion. And this is why, by the way, I raised the issue of syntax versus semantics, because the counterexample method is based on this distinction. Now here's an example. It's in predicate logic. We have two premises and a conclusion. The first thing we're going to do is to translate this, so to speak, into a more ordinary language form. So for premise 1, we have for all x, if x is an h, then x is a t. This is the same thing as all h's are T's. The second premise, we have no D's are H's, and the conclusion is, therefore, no D's are T's. The goal is just to substitute something for H, something for T, something for D, and to be, of course, consistent. The easiest way to do this is just to, pick easy things. Substitute things like animals, humans, dogs, cats, plants, and so on and so forth. So let's try this. For the first premise, we'll say all humans are animals. And this is a true premise. So we substitute humans for H and animals for T. Second premise, we have no, let's try dogs. No dogs are humans. So D for dogs. And the premise is also true. Our conclusion, we have no, D, so no dogs are T's, which happens to be animals. So we have no dogs are animals, but that's clearly, uncontroversially, a false proposition, is a false conclusion. So we have two true premises, but a false conclusion. So this argument here is invalid. And so this argument here must likewise be invalid. We've used semantic content to show that syntactic content is invalid. It's pretty simple, but of course some arguments can become very, very complicated, and it's not always so easy to know what to substitute. But the best way to go about this, in my mind, is just to choose very simple things and then go from there. But like anything, it does take some practice. The Finite Universe Method is another way to test for invalidity. Now, validity and invalidity remain the same no matter what universe or so-called possible world. The term possible world is just a term that logicians and philosophers use. For example, I'm contingent, I can exist, and it's possible that I didn't exist if my parents did not conceive me. So there's a possible world, we might say, that I do not exist, and in this world, this possible world, I do exist. On the other hand, a statement such as 2 + 2 = 4 is true in every possible world. It will be true even in the possible world in which I didn't exist. And likewise, if we think about validity and invalidity, because these are, basic, let's say, structures of logic, okay? If we think about the syntactic content of logic, there are certain forms that are just valid and certain forms are just invalid. And this is going to be the case in every possible world just as much as 2 + 2 = 4 is going to be true in every possible world. At any rate, with this finite universe method, we're going to convert a predicate argument into a finite universe equivalent. So here's the basic idea. This finite universe will contain n number of things. A finite universe may only have one thing. It may have 2 things or 3 things. Now, n, the number of variables, are going to be given existential names. For example, if we have 2 things in the universe, we'll say we have something that's A and then something that is B. The question then becomes, how can we translate universals and particulars, namely existentials? Okay. Now, if there's only one object in this finite universe, we could just clearly state that. It's pretty straightforward. If we say, for example, for all x, x is an f, if there's only one thing in the universe, we can just say fa, that a is an f. And likewise, if we have there exists some x such that x is an f, we can say, well, if there's only one thing in this finite universe, this is just equivalent to fa. But what if we have two things? If we're talking about everything that exists, we're going to have to say that. So we'll say fa and fb. So here is the statement we would derive from this for all x, x is an f, if there are only two things in the universe. Now, in regards to an existential or particular claim, we would say fa or fb. Okay. There exists some x such that x is an f. Because we're dealing with some, we can say, well, because there's only two things, it's either fa or fb. And that's why I say that universals always will use conjunctions, particulars will always use disjunctions. And then we're going to be using the indirect truth table method to test for invalidity. Okay, so we're going to start with a universe of one thing and see if we can get an invalid argument. If that doesn't work, we can try two things or three things, etc. And remember, of course, an invalid argument will have a false conclusion but true premises. Let's think about a concrete example because that's the best way to learn this. So we have this argument, two premises, and a conclusion. We're going to try a universe with only one thing in it. Okay, so let's say we have n equals 1. There's only one thing, and we'll call that A. So we're going to translate this into this finite universe with only one thing. So the first premise we have for all x, if x is an A, that x is a B, what will that be equivalent to? We'll just substitute A for x. So we'll say AA arrow BA. So this is premise 1. For premise 2, we'll get CA arrow BA. And then for our conclusion, we'll get AA arrow CA. And with this indirect truth table method, I'm going to create a table. So some statements perhaps we'll say are true and some perhaps as false. Okay. We want to see if we can set up this argument such that the premises are true but the conclusion is false. Let's look at the conclusion first. We want that to be false. So what could we do? Well, it's a conditional. If AA, then CA. The only way that that can be false is if we have a true antecedent but a false consequent. So AA is true, CA is false. So we have a false conclusion here. And now we can look at our premises. So we said AA is true, and we said CA is false. And now let's see if we can get the first two premises true. So BA we can say is true. Let's just try that. So we'll say this is true. Well, if we have a true antecedent, true consequent, we have a true premise. And if we have a false antecedent and a true consequent, we still have a true premise. So just with one thing in this universe, we're able to show that we have an invalid argument. If this argument here is invalid in a finite universe with only one thing, that's one possible world, it's also going to be invalid for any other possible world. Hence, we conclude that this argument is invalid. We'll look at another example. We have two premises, a conclusion. We'll try a possible finite universe with one thing. Our first task is to convert this to a finite universe. We have a first premise. Because there's only one thing, We'll call that A. So we'll substitute A for X. Hence we have MA, arrow LA. Next we have RA and LA. And then our conclusion, RA and is not the case, MA. We have our table of values, true and false. We want a false conclusion. We'll try RA is false and MA is true. MA is being denied, so that turns into something that's false. False and false, and in conjunction is just false, so we have a false conclusion. RA is false, MA is true. We're already in trouble because in our second premise, we want this to be true, and we have one of those options, so to speak, as false. So how about we make RA true instead. If we look at our conclusion, we have true and false. That's still false, so we're good there. So RA is true, and we'll say LA is true. So we have a true premise here, and a true premise here. Hence, we can see the argument is invalid. I was hoping this would require two members. I thought that it did, but okay. Hopefully the next one will. But let's say this didn't work. What would we do if the universe had two things in it? Okay, so how would we convert premise 1 into a finite universe with two members? Note that we have a universal, so it's going to be a conjunction. So we'll say parentheses MA, arrow LA, and parentheses MB, arrow LB. Okay, so if we have a finite universe of 2 of A, B. What about the second premise? It is a particular existential, so we'll have a disjunction. So we'll say RA and LA, or RB and LB. And for the conclusion, we have another existential, so it will be a disjunction. Okay, so on and so. Sorry about that, I tapped the screen a little bit too soon. Let's just work on the next example, our final example. We have this argument, and we will convert this to a possible world, a finite universe with only one object, so n equals 1. We'll call that A. And hopefully this time we will require at least two things. I'm pretty sure we need two things here. That one thing will not work, but let's just make sure. And because there's only one thing, A, we'll just substitute A into the variable x. Hence the first premise, not MA and RA. Second premise, not RA and LA. Conclusion, therefore, not LA and MA. I'll create a true-false table to track our values. We want a conclusion that's false. Hence, let's just try LA is true and MA is true and see what happens. LA is being denied, so that's false. We have a conjunction, false and true is false. So that's good, we have a false conclusion. LA is true, MA is true. Well, we've already run into a difficulty because we have this not MA, so this will turn to something that's false, but there's a conjunction there. We want both, so to speak, options to be true, so to make premise 1 true, we need MA as false. So let's correct that. So MA is false. The conclusion is still false, so that's good. So premise 1, not MA, true. Now RA has to be true in order for this conjunction to be true, to get a true premise. However, with premise 2, we have this not RA. If we say RA is true, and that's being denied, we get something that's false, we will get a false premise there. If we say RA is true, we will have premise 1 is true, but premise 2 is false. On the other hand, if we say RA is false, we'll get premise 2 as true and premise 1 is false. So we're stuck. There's no way to show this argument is invalid in a world with only one object. So we need to move on to something else. Let's say that n equals 2. We have two objects, A and B. We have our first premise. We want to convert those, translate those, so to speak, into this finite universe of two objects. It's an existential or particular, so there'll be a disjunction. We'll say not MA and RA, or for the second object, not MB or RB. Premise 2, another existential or particular, hence it will be a disjunction once again. So not RA and LA, or disjunction, not RB and LB. And our conclusion, we have another existential or particular, hence a disjunction, not LA and MA, or not LB and MB. We want that conclusion to be false, so let's try LA as true and MA as false. Okay, because this is a disjunction, so both options will have to be false at the end. Okay, so LA is being denied, so that turns into something that's false, and then we have this conjunction false and false is false. And likewise, if we look at this not LB and MB, if we say MB is false, we would have to say, well, we don't have to, but we can just try LB as true. So that's false now. False and false is false, and false or false is false. So that is definitely what we want. We have a false conclusion. So I am saying LA is true, that LB is true, that MA is false, and MB is false. Okay, so LB, now let's work on first premise. So MA is false, RA, we haven't decided that yet, MB is false. Let's see, second premise, we have an LA, that's true, and a LB is true. Back to the first premise. Here we're not going to have any difficulties to get that true, I don't think. So we'll just say that RA is false, and we'll say RB is true. So MA is being denied, that's true. True and false is false. MB is being denied, so that's true. True or true is true. False or true as a disjunction is true, so this is a true premise. If we look at our second premise, Again, I don't think we'll have any difficulties here to get something that's true out of that. So let's see. We'll say RA is false. That's being denied. That's true. True and true is true. If we say RB is true, that's being denied, so that's false. False and true is false, but true or false is true, so this is a true premise. And we said that RA is false, RB is true. We have a true premise, false conclusion. The only way that's possible is if the argument is invalid, thus the argument is invalid. If n equals 2, in this possible world, the argument is invalid. So in any possible world, the argument is invalid. Thus, our original argument is invalid. Up next, we will return back to the Suppes and Hill textbook, 6.3 Logic of Identity. If you like this video, please consider supporting my work at amateurlogician.com.